Hello everyone. Good afternoon here in the room and on Zoom. So today we're going to move on to a new topic. In the last lab, we looked at using our own personal computers for doing some processing of data, counting words and counting n-grams and so forth. So today we're going to start to think about using multiple computers. And this gives rise to the notion of a distributed system. So if we want to process large amounts of data, often we're going to need to use multiple machines. And for this, we will need some distributed systems. So we spoke about the difference between these two options, having one machine that's n times as powerful, like this supercomputer Cray type machine, and n machines that are equally as powerful. And we mentioned that often we would like to use n machines that are equally as powerful. It has the nice advantage that if we need more computing power, we can add more machines, right? Whereas it's difficult to extend one machine to be more powerful. So in terms of distributed systems, what we can talk about are two different types of systems. We can talk about a parallel system and a distributed system. So in a parallel system, often we'll have multiple processors that can process data or process instructions in parallel. Your notebooks are probably, your laptops are probably parallel machines in some sense because they have shared memory and multiple cores if you have a multi-core CPU. Yeah. So we can have a massively parallel system with many processors, possibly even many CPUs with many cores, or GPUs and so forth. When we talk about distributed systems, we talk about shared nothing. The computers, the elements of the system don't share anything. They're independent computers. So we see that each machine has its processor. It could also have multiple processors. And it shares memory within each machine, but the machines themselves, the overall distributed system, is composed of computers that share nothing. They're independent computers. So it would be like connecting independent computers by a network, by Ethernet, for example. Yeah. So these are independent computers that are networked effectively. So what is a distributed system? A distributed system is a system that enables a collection of independent computers to communicate in order to solve a common goal. Yeah, this is the simple definition of a distributed system. There are courses, entire courses just on distributed systems. The focus here is more on processing data, but we will be seeing a lot of distributed systems used for processing large amounts of data. Today's class, I want to give you an introduction to some concepts, some challenges, some ideas, and also give some preparation for the lab that we will see on Wednesday. Yeah. So a distributed system is a system that enables a collection of independent computers that are networked to communicate in order to solve a common goal. Yeah. They have three important properties. Some people name more properties, but these are the three key properties. Concurrency, which means that the computers, the machines are doing work in parallel. Yeah, they're working away, they're doing their tasks in parallel. Second is independent failures. This is the idea that one of the machines, one of the components or elements of the distributed system can fail, and that this does not necessarily mean that the distributed system is Parece que hemos regresado de nuevo. So we're back. Arisen from the dead. I have to share my screen again. Can you hear me? All good? So you can see my screen? Yeah. Okay. And we're still recording. Okay. Okay. Let me just check my audio settings. Let's see. Yeah, should be fine. Okay. So we have independent failures, which means that one part of the distributed system can fail, but it doesn't mean that the distributed system itself will fail entirely. Yep. Third aspect, which is a bit abstract, but it means, well, the third aspect is that there is no global clock. Each machine has its own clock. Try as hard as we might try to synchronize the clocks, the CPU clocks, as best as we can, but each component will have its own clock. Each machine will have its own clock, and we can't assume that we have one clock, right, to synchronize everything. What does this mean? It means that we have to rely in distributed systems on asynchronous communication. Yeah. So it means we're going to have queues of things that we're going to have to process. We're going to have asynchronous communication where we don't know how long it will take for a message to be received, how long it will take to process something. Okay. So we have no global clock. We can get the clocks pretty good, like as in human coordination. If we all have watches, our watches will be slightly different, but we still turned up at the same time here today, right? So we can do things, but we can't assume to have a single consistent clock, right? So there will be slight differences, which means asynchronous communication. Any question or comments so far? So this last part has some particular challenges. So I think it's useful to look at some of those challenges to understand the need for fault tolerance, replication, and all sorts of stuff that we'll see later. So in terms of the challenges of distributed systems, there's this problem, which is quite famous in computer science. It's called the two generals problem. The problem has nothing to do with computer science superficially, but it has some clear analogies. The idea is that we have two generals who have two armies that are split up, right? And what the generals would like to do is to coordinate. They want to coordinate their attacks so they can attack together. But we see that they're in different places, right? So they also have, there is no global clock, okay? So the two generals need to agree on a time to attack. They can send messengers on horseback, but these messengers can be killed on the way, en route, right? How can the generals coordinate a time for attack? Let's simplify it and say that this general here is the one who would like to propose a time. Says 12:50. We're going to attack at 12:50. So they want to attack together to have the best effectiveness for the attack. So what can the first general do? The first general says, okay, 12:50, let's go. Right? So what does the general have to do? Has to send a message to the other general. Yep. Yeah. Send a message to the other general. So sends a messenger on horseback. The problem is that they have to cross through this terrain here where the messengers can be killed, right? So how can the generals coordinate a time for the attack? Well, the first general sends a message with the time to the second general. Yeah. We good? Yeah. Right. Okay. So you say that in this case here, essentially, the first general doesn't know if the second general received the message or not. So he could, if the second general doesn't receive the message, if that messenger was killed, the first general will attack and the second one won't, right? Which is a disaster in this scenario, right? They both have to attack together. So your idea is that the second messenger or the second general should send back a message, right? To say, I received the message. Yeah, 12:50. We're good to go. Yeah. So now we're good, right? Problem solved. No? Why not? What's the problem? Now the second general doesn't know if the first general has received the confirmation. So the second general is wondering, should he go or not? Should he send the troops into the attack? Because if the first general hasn't received the confirmation, they may not attack at that time, right? So what's the solution? Easy. First general sends an acknowledgement back to the second general. Yeah? Done? We all happy? No. No, it's easy. In this case, the second general sends back a confirmation to the first general. Yeah. And so on and so forth. So how can we solve this problem? So this is called the two generals problem. How do we solve this problem where we don't need an infinite sequence of acknowledgements of the previous message? Any ideas? Well, there's no ideas, and that's probably because we can't. There's no solution to this problem. This problem is unsolvable. Yeah. Maybe slightly depressing, but such is life. Yeah. So obviously, when we're talking about the two generals problem, we're kind of referring to distributed systems. Yeah. So instead of generals, we have computers, and the computers somehow need to coordinate to agree on something, right? So there are certain, it's unsolvable. We can't solve this in a general case, but we can try to build our distributed system in such a way that we mitigate or reduce the probability of problems. That's the best we can do. Yeah. So we can try to improve the communication reliability, try to improve the reliability of the network in this case that the machines are sending messages through. As we see, that's still work in progress as the Zoom call failed about 10 minutes ago. So we can try to improve the networks. We can try to build our distributed system, keeping in mind that communication is unreliable. So we can try to avoid catastrophic failure if for some reason there are problems with communication. We can use something like idempotency. Why is this so difficult? Idempotency tokens. What are these tokens? Essentially, they indicate the content of a message. So in the context, let's say, of a bank transaction, or if you wanted to buy something and maybe the payment fails and you don't know if the payment was received on the other side. I don't know if this has happened to you. You're buying something online, you put in the details of your card, you hit buy, and then somehow there's a failure and you don't know if it's gone through or not, right? So maybe you might try to buy the same thing twice. These idempotency tokens, what they do is they have, for example, a session ID. They have some information of the products you are trying to buy, and if you try to buy the same thing twice, it will reject it, right? Even if it was received on their end. Yeah. So it's essentially to avoid acting upon repeated requests where you buy the same thing twice. We can also think maybe about predefining default values, something that we default to if we detect there's communication problems, and so forth. But there is no solution to this. Yeah. So this is the two generals problem. There is another problem, a related problem called the Byzantine generals problem. It's a little bit different. It's a similar scenario. Why people in distributed systems talk about generals all the time, I'm not sure. But in this case, we have many generals, and they need to agree on whether to attack or retreat. They must attack or retreat in unison, and as before, they're remotely located, so they need to send messengers. They must decide on whether to attack or retreat in unison. If some of them attack and some of them retreat, there's going to be trouble, right? So they have to coordinate to decide which action to go upon. They can send messengers again on horseback, but the difference is that this time the messengers can be replaced with spies. So in each camp, there is spies, and they can somehow take over the messengers, yeah, and send a false message or send whatever message they want. These spies are working for the enemy, yeah. Okay, so let's say that the first general decides to attack. First general decides to attack and submits to the other two generals the attack signal, yeah, by messenger. The second general decides to retreat and sends, so this is asynchronous communication. So they still hasn't received the attack message from the first general, but decides to retreat and sends that message to the other two generals. Yeah. The third general decides to attack, sends the attack message to the second general. Yeah. But the message sent to the first general is intercepted by a spy. So what would you as a spy decide to send? So one thing to mention, sorry, is they've decided that they will go with the majority. Yeah, so they'll decide whatever the majority is, that's the option they're going to go for. So what would you as a spy, if you wanted to interrupt these generals' plans, what would you send? Retreat, right? You'll send a retreat message. So what should the spy do? The spy should retreat. Yeah. So what happens in this case? So what happens is that the general on the left will attack, right? Why that general actually wanted to retreat, but has received 2 attack messages. So the 2 attack override the 1 retreat. Yeah. What will the general in the middle do? Attack. That general wanted to attack and has received another attack message as well as a retreat message. 2 attacks, 1 retreat, right? So that general will attack. And what will the rightmost general do? Retreat. That general wanted to attack, but received 2 retreat messages that overrides the 1 attack. So this general will decide to retreat and disaster will ensue, right? So this is called the Byzantine general's problem. And the type of error is different. It's not just that the messenger fails to get through, it's that the messenger can send the wrong message, right? So somehow the messages can be viewed in different ways by different parts of the system. So again, this is a problem for distributed systems. Yeah, we might have maybe different versions of software. There might be some communication fault where some data gets garbled. We might have some old entry in our database that we're reading that is hasn't been updated yet because we're receiving lots of updates. So these Byzantine problems basically involve not having the same view of a particular value. For example, what's the opinion of a general? Yeah, there are 2 nodes in the distributed system that have 2 different views of the same thing. So to solve this, there is no general solution, but we can at least apply some mitigation again. So we can apply some sort of consensus protocols to say that we're going to take a majority vote. We're going to also, for example, we could get the machines to send in multiple rounds information. So for some, if in some case, these 2 machines could communicate and say that this 3rd machine here, the bottom machine has, if they could detect that it has sent them different messages, then it could come to a better resolution, right? So we could go in multiple rounds. Yeah. So there are ways, again, in practice where we can mitigate these sorts of problems, but a general, a full solution is somehow impossible. Yeah. We can at least be robust in the sense that if we have 3 machines, we could be robust to 1 Byzantine fault. Yeah. So long as the majority are okay using consensus protocols. So we can be robust up to a certain number of these kinds of faults. We can also, send multiple messages and also maybe think about null messages where there's uncertainty. We don't know what to send. We can send a null message that essentially doesn't count in the vote. Any questions or doubts? So the core message here is that distributed systems are difficult to build, and we have to take into account the different types of faults and problems that we can have. Like the 2 generals problem, the Byzantine generals problem. Yeah. So we'll see some of this later in the course about how we can deal, what kinds of errors we can have, and how we can deal with these using different design choices. So next we're going to talk about what makes a good distributed system. A good distributed system, because we have all of these machines and network and all of these complications, a good distributed system should provide a level of abstraction for us. So rather than the client having to know on which machine or which machine is doing a particular task or stores a particular piece of data, what we want is that the machine somehow appears, the distributed system appears abstractly as if it were 1 system. Yeah. So this is called transparency. So when you search for Google, you do a Google search, you don't say what machines you want to run your Google search for you or what machines they have to query. On what machines are the documents you might be interested in. You just run a search, right? Google just looks like 1 system, but behind Google, there are thousands upon thousands upon thousands of machines. Yeah, you don't have to care about that. Yeah. So essentially, there should be some sort of layer of transparency such that the system looks like 1 system. Another thing, if we want to extend, one of the major benefits of distributed systems like this is that we can add more computing power by adding a new machine. So we'll say that a distributed system, a good distributed system should be flexible. Yeah, we should be able to just plug and play. So we add in a new machine and it gets included into the distributed system and gets put to use immediately. Yeah, without some major configurations or changes to the operation of the distributed system. And the distributed system ideally should continue operating as normally while this is happening. So we should be able to add and remove machines quickly and easily. Third good aspect of a good distributed system is, of course, the idea of reliability, that the system will continue to work even in the case of a failure, right? So it's somehow robust to the failure of an individual machine or node in the distributed system, right? So Google doesn't fall down every time a machine in Google fails, for example. So we have to assume that there will be faults. Performance, okay, does stuff quickly. So whatever we're processing, of course, that we have the distributed system is doing things efficiently. It's load balancing. It's making sure that it's making the best of its resources in order to ensure good performance. And scalability. So we want to ensure that the infrastructure scales. So what does that mean? It means that, okay, on one side, we want to be able to maybe add more and more and more machines, maybe in different locations. So our system should be able to cope with that. Not just that, but also, it's a very long animation. Also, not just scalability on the infrastructure side, but also, okay, one more. One massive distributed system. Also on the client side. So we want to be able to deal with lots and lots and lots of clients as well. And one more, I'm sure. There we go. So these are some aspects to keep in mind when we're designing distributed systems. Transparency, flexibility, reliability, performance, and scalability. And as we see, some of these are quite challenging to implement in distributed systems, taking in mind, for example, the problems, the challenges we saw earlier. Doubts, questions? Okay, so we're going to move on to talk about two different main types of distributed system architectures or paradigms. The first one is called a client-server architecture. So it's maybe as the name suggests, you might guess. Client-server model, basically, client makes a request to a server, and server acts and responds. So somehow there's the client who has some need, and there's a server that can service that need, right? That provides the service. So this is a pretty typical distributed system. Any examples of client-server model? So the web, for example, we have web servers, we have clients which are like browsers or whatever. Email, yeah. Banks, Dropbox. Yeah. Some examples of client-server type interaction. So just to mention that one common type of sub-architecture, and client-server is a very broad idea. So just to mention that there are different types of client-server architecture. One would be, for example, a three-tier server where we have a presentation layer that somehow receives requests from the user. We have logic, which can take care of the logic, the processing of the application. We have a data layer that's like the database. Yeah. So then on the way back, the logic applies some aggregation to the data, and the presentation then creates some sort of interface or visualization of the results for the client. Yeah, so this is one example of a more specific type of client-server architecture. Okay. So this is called three-layer architecture or three-tier architecture, data, logic, presentation. Yeah. It's important to note here that when we talk about a server, we're not necessarily talking about one machine, right? A server here can be a distributed system. We could have multiple machines maybe for the data layer, we could have multiple machines for the logic layer, multiple machines for the presentation layer, or maybe if we have a smaller distributed system, every machine could take part of the responsibility of each layer. Okay, questions? Okay, so we can contrast this client-server architecture with something called a peer-to-peer architecture. Have you heard of peer-to-peer? No? Yeah, BitTorrent, okay, yeah. So what we have in peer-to-peer is a client-server architecture where there's somehow this one machine that has this special role that is the server. I mean, we get all these, not one machine, but one component of the distributed system. It can have multiple machines, but it's a server, right? And we get multiple clients that can query the server and get responses back. On the other hand, we have peer-to-peer, where essentially peers are somehow more equal, right? So they interact directly with each other and there's no server as such. If there is a server, every component of the peer-to-peer system is both a server and a client, yeah? So in this case, we have many clients and one server. In this case, every component essentially has both a client and a server. Yeah. So they all kind of take on the role of providing the service. Examples of peer-to-peer systems. Somebody already mentioned BitTorrent. Any other examples of peer-to-peer systems? So Bitcoin. We don't have a central bank anymore, right? We're sharing as peers somehow. That's the idea of many cryptocurrencies, is that they're peer-to-peer. Yeah, you're acting not just as the customer of the bank, but the bank itself. Yeah. Bitcoin, BitTorrent, anything that starts with bit, right? So for Dropbox, here on the left, we have the file server, right? So this is a Dropbox server, and we have all these clients that are reading and writing files. Yeah. So what would a peer-to-peer equivalent of Dropbox be? It would be BitTorrent, right? So peer-to-peer file sharing, such as BitTorrent. Yeah. So what's the idea here? Peers act both as the file server and the client. So peers both act to download data, to get data from other peers, but also to serve data to other peers. Yeah. So this is peer-to-peer idea. Yeah. So every person who's participating in BitTorrent is seeding and leeching, or should be at least. Yeah. So leeching, downloading, client, and seeding, serving data. Yeah. Server. Online banking. Clients interact with a central banking server, and a peer-to-peer equivalent of that would be Bitcoin, as we mentioned. Yeah. So peers act both as the bank and the client somehow. Yeah. So maybe this one's a bit more deep cut, but SVN, subversion. Anyone remember subversion? Anyone know subversion? So subversion is a versioning tool. Yeah. Very similar to what the peer-to-peer version is, which you would know as Git. So many of you would have heard of Git and GitHub and so forth, right? So subversion was a client server type paradigm for versioning, where there was one central server and that would manage the version repository. So all the clients could push and pull from that central repository. The change in Git, one of the main changes in Git was that everybody has now their own repositories, which they sync. Yeah, so they take care of their own versioning. Yeah, and there's this sync way to combine or to make two repositories coincide. Okay. Any questions or doubts? Okay. So we have in peer-to-peer, we often consider scenarios that are highly heterogeneous. So somehow the idea is that we have different types of devices. Yeah. So for example, if you look at BitTorrent, you could have mobile phones anywhere between a mobile phone and a massive server that are participating in this peer-to-peer system. So we have all sorts of different types of devices in a peer-to-peer system, often, not always. And what we'd like to do is somehow structure the communication in this peer-to-peer system. So the very basic peer-to-peer system is called the unstructured peer-to-peer system. Yeah. And we're going to take an example of an illegal file sharing application where we have every node has some data, some albums, some music, some videos, whatever it might be, and the peers want to share them. Yeah. So in the unstructured setting, each peer is connected to some of its peers, maybe some friends that they know, right, that they have the information for. So their friend contacts them and says, hey, there's this cool peer-to-peer site where you can get Ricky Martin's new album, for example, and then they connect. Yep. So in this way, we have an unstructured peer-to-peer system. Yeah. So just organically, people connect, peers connect to other peers, depending on who they know in real life, for example. So there's this node who wants to know, where can I find Ricky Martin's new album? I would like to get access to that. So how would that node find this album in this unstructured peer-to-peer? So what's the one thing you can do? Right.
Checking all the neighbors.
Yeah, I do.
And
Yeah, similar to DFS. Yeah, that's similar. So okay, we assume that these peers have the albums, right? So the one who's looking for the album, they can try something like a DFS, a depth first search. Yeah, they'd ask their neighbors, hey, do you have this, or do you know somebody who has this? And those neighbors pass on that request and they say, actually, I do. Yeah, in this case. Yeah. So in this case, it's fairly straightforward because there's a neighbor who directly has it. So after that, those two peers or nodes or elements can form a connection and share the information. Yeah. If there's maybe an album that's more obscure that less people have, then of course this could get a little bit more complicated, right? So we assume in this case that there's only one peer in this peer-to-peer system that has the album. So then they need to ask their neighbors, their friends, and those friends have to ask their friends, their neighbors in the network, and so on and so forth until the album is found or not found. Yeah. And then direct connection can be set up between the two. Yeah. So they can share some IP information so they don't end up sending all the data back through the path. Yeah. So this would be unstructured peer-to-peer system. Yeah, this is the kind of basic, no structure, people connect however they like. We have no central server, right? So, and the way of finding things is called flooding. Essentially, to find anything in this network, we need to sometimes flood the network to find what we're looking for. Okay. So if we compare this to another type of peer-to-peer architecture, which looks a little bit like a client server, and it has elements of a client server architecture, what we're going to have is a central server, yep, where each peer registers themselves with the central server. So essentially every peer says, hey, I'm interested in participating in this peer-to-peer system. Here's my, here's what I have. This is the content I have. I have Ricky Martin's new album. I have the Pixies new album, whatever. And here's my address. Here's my IP address where other peers can contact them. Yeah. The peer then requests content from the server. So if I want Ricky Martin's new album, I ask the central server, the central directory. Hey, I want this. What can the central server tell me? It can tell me directly, hey, you should talk to this other peer. Yeah, down below. So it can give, the central server can give me the address of peers that have or claim to have that content. And then the peers connect directly. So this was a pretty common infrastructure for peer-to-peer file sharing back in the day. Why? So it's quite a lot more efficient than what we saw with the unstructured aspect. Yeah. Yeah.
What if we have like many servers that are constructed, like the same problem?
So yeah. So if you had many servers like these central servers that were unstructured, there's another kind of topology of peer-to-peer that we'll talk about, but it goes in the way of supernodes. So there are other types of peer-to-peer system, maybe between universities, where the university has their own instance of something like Mastodon or one of these video class platforms, for example, or maybe even for LaTeX packages or whatever. There are mirrors in different locations that act like super peers, and they communicate and synchronize amongst each other, and then they share kind of information with the local population, which are normal peers. So it goes maybe in that direction a little bit if you had multiple of these that were networked, multiple of the central servers. Yeah.
Which famous system will use this? Which famous system will use this?
So Napster was the famous one. Yeah. So we'll come to that in a second. Yeah. Okay. So any advantages or disadvantages of this?
if the server dies, the whole network.
Yeah, so the server is what we call this thing in the black box here is what we call a single point of failure. Yeah, if that server fails, and by the way, just to mention again, when I say server here, I might be given the idea that it's one machine, but it could be multiple machines. It's just in one location. Yeah. So if this server dies, then the whole system goes down. Yeah. What are some advantages? Yep, it's a lot faster than the unstructured case. Yeah. Security as well. Yeah, at least we don't have to maybe upload our content or our files to the central server. Yeah. Also, from the server point of view, the server doesn't actually have to manage massive amounts of storage. The peers are storing the data, right? So the storage is completely decentralized. So the costs for the server are pretty low. To run a server like this is not really that costly. Yeah. You just have to be able to manage some directory of information about peers and what content they have. The major disadvantage is the single point of failure. Yeah, so there were a number of file sharing sites, for example, Napster, which ran on this model. Does anyone remember Napster? Might have heard of it. Nobody wants to admit it. We're all being recorded. I've never heard of Napster. So what happened with Napster? They went with this technology. And the good thing is they actually, as a central server, not only is it good that they don't have to store the files from a storage point of view, they don't need massive disks. It's also good from a legal point of view because they can just claim that they're a mediator of file exchange. Yeah, they don't actually host any content themselves. They just connect users. Yeah. However, they eventually lost that argument. And basically Napster was shut down. Yeah, so the authorities came and they shot the server. They brought the server around the back of the barn and shot the central index server. And with that, Napster died. Yeah. So that was the end of Napster. So another type of structure we can have, maybe somehow mixing between having the central index or central repository that manages all the information of the peers. We can have some sort of hierarchical structure where we have super peers and peers. This is common for different types of academic institutions, for example, as I mentioned, where they can host mirrors of LaTeX packages or of Linux packages, Debian packages, where you have all these servers in different locations, mirrors that you can choose from, and then you can share. So that's a more mirror type architecture. One could also see this maybe in Bitcoin, where you have maybe some peers that are managing or looking at the entire blockchain, or maybe even mining as well. They have a slightly different role. They have more responsibility in the peer-to-peer. And then you have these wallets or these peers that are just, doing very little except for tracking their own information. So advantages and disadvantages of this. So it's sort of like a balance between completely unstructured and the central directory. Yeah, it's not as efficient, but we get some benefits. There's some structure. Yeah. And we also have to find some people have to volunteer, there has to be some incentive for people to be super peers, right? For these people to do more work than other peers in the network. Another type of approach, and the last one we'll look at for peer-to-peer, is something called a structured approach. And the idea is that we're going to look at these peers as if they were buckets in a hash table. Yeah, as if they were essentially data structures. Yeah. So we form a data structure somehow over all of the peers. A very common type of data structure that we'll use is a distributed hash table, where effectively we create these buckets. Yeah, like in a hash table, and depending on the hash of something, we're going to assign that content to a particular peer. So we have essentially our data organized as key value pairs. The key might be the name of the album or something like that, and the value could be the actual songs themselves. We hash on the key, and we insert the data with the key value. Yeah. So essentially each peer is managing a key range. Yeah. So for example, there's some peers managing all the things that happen to have a key with hash that starts with 000, another peer with managing all the content with 001, and so forth. So if the Ricky Martin's new album, the hash that we use starts with 000, for example, then it will be indexed, copied, replicated on these peers here. With a hash 111, the Pixies album would be stored here. Advantages, disadvantages. Major advantage here. Yeah, so we can find out much more efficiently now which peers have which data using the hash. Yeah. The disadvantage, major disadvantage. We're imposing a structure, which means it means that the peers have no longer control over what they store. Yeah. Before in the unstructured, people could just naturally have whatever data they're interested in on their hard drive. Yeah. Now we're forcing peers to somehow index certain content based on the hash. Yeah. So we have to impose a structure on the peer-to-peer network. So this would not be good for a typical file sharing application, but it might be good for other types of applications. Yeah. Okay, so this is called a distributed hash table. And we're going to be seeing similar concepts again later in the course in NoSQL systems. Okay, so in terms of how to connect the peers in a structured peer-to-peer system in terms of a distributed hash table. So here we show the kind of hash structure, right? But how are these peers actually connected? So a typical way would be to create a circular DHT, right? So we don't want all of the neighbors to have to know all of the neighbors, but somehow we create a circular DHT so that each peer or each set of peers is aware of whoever is in their hash space and their neighbors. Yeah, those peers that share the same hash range and the neighbors, right? So the ones that are one off, let's say. So this allows us to do O(n) lookups, which is not much better than in the worst case than doing unstructured. However, if we wanted to, so for example, for the O(n) lookup, Pixie's new album, if we're on the hash range is at the other side of the circle, we have to go around and talk to half the neighbors, right? However, what we can do afterwards is again establish a direct data connection so that we don't have to send the data back through all of the neighbors. Yeah. If we want to make this more efficient, what we can do is implement shortcuts in the circular DHT. Yeah, so we can have like a sort of snakes and ladders. Well, I don't know, it's really like snakes and ladders. But we can create bridges from one side of the circle to the other that can allow for skipping neighbors, right? So in this case, if the same peer asks again for the Pixies new album, they can use the shortcut this time to find that after 2 hops. Yeah. So this can greatly reduce the number of neighbors or number of peers that need to be queried. So we have all these different recipes for client server peer-to-peer style architectures. One thing that's important for peer-to-peer systems as well is to be able to handle, for example, peers leaving. So this is often called churn. So if you imagine if you're using any typical peer-to-peer system, for example, if you're using BitTorrent, right? If you leave, then all the data you have is no longer accessible while you're not using BitTorrent. Yeah. So maybe some new users come in, right? So something like BitTorrent would be an example of a peer-to-peer system that has a high amount of churn, of peers leaving and peers coming back in, coming back into the network. So the idea is, if we want to maintain a robust peer-to-peer structured DHT, we should have access not just to neighbors and shortcuts, but we should also keep about n successors so that we can essentially jump over anyone who's left. Because in this case, if one of these peers leaves and they're in this perfect circle here, then it means that the circle will be broken and there will be problems with the DHT. So in order to increase robustness, we can keep n successors. So it can be 2, it can be 3, it can be 4. The more successors, the better for the robustness of the DHT, but the more connections we need to manage, right? So new peers then, when they join, they can fill in the gaps for the old peers. Of course, if we want to have a particularly robust DHT, we shouldn't have one peer per hash range. We should try to replicate and make sure we have multiple peers covering each hash range. Questions? Okay, so we'll look at a real life example of a distributed system. So we've looked at client server architecture and peer-to-peer architecture. But in reality, in practice, these are often abstractions. Often we're going to mix and match. We're just going to do whatever makes sense. So most practical systems are going to have elements of client server and are going to have elements of peer-to-peer. Yeah. So if we look at a real world example of a distributed system that mixes both, we can look at BitTorrent, right? We already saw something like that with Napster. BitTorrent has been around a lot longer. So the idea of BitTorrent is that we have this server, which could be maybe just one machine, that has a file with 6 parts. Yeah. So we have the 6 colored blocks here. Then we have other clients who want to access that file. They want to copy that file. There may be multiple such clients who are interested in accessing the file. So in the client server model, each client would just ask the server and the server would return the data and we're done. Yeah, that's not what we're going to do here. We're going to try and find a more efficient way to share the data. So what the machine that has the data does first, we're going to assume it's Ricky Martin's new album, and we can say every block here is a song of the album or whatever. They're going to create a description of the album. What are the files in it? How big are the files? What's the name? What are the tracks? Whatever it might be. What's the audio quality? And some information about how they can be contacted. Yeah, some networking information. They submit that torrent file to some sort of torrent site. Yeah, some BitTorrent search server. Okay. So this client is interested in Ricky Martin's new album, goes to the search site, searches for Ricky Martin, and receives this result, which is, hey, we have this torrent file. So they download that torrent file. That torrent file includes a description on how to connect to this peer here. Yeah. So after that, there is a DHT, a distributed hash table. So we use a peer-to-peer, not for saying which peers should store which files, like if they should store which album. We use it, however, for tracking the peers in the system. So there's a DHT distributed hash table, which amongst the peers is used to track information about which peers are active and which peers are not. What are their IP addresses? How can they be connected? What are they? Whoever is interested in this torrent, right? Whoever is actively using this torrent, either to download, to leech, or to upload, to see. So with the DHT, peers get information about each other, and then they start to share files. So rather than the one server that has everything, this one peer that has everything, serving all of the data to one peer and then that peer copying it on to the next person, it makes a lot more sense to copy blocks, right? So if I had a stack of 100 pages here that we had to photocopy, let's say, I don't know, you could use your phones to copy them, or you each had a copier, rather than me copying 100 pages and handing you 100 pages and then you copying 100 pages and handing them on, it would make sense if we started to distribute, right? So maybe each of you copies one page and then you share that page with somebody else, right? So each of you starts at one page and you start sharing the pages amongst yourselves. So this is how BitTorrent operates for file sharing. So everybody has their Ricky Martin's new album. Everyone's happy. So in terms of BitTorrent, how does it work in the client server peer-to-peer architecture? The part where they create a torrent file, okay, that's local. That's something someone has to do on their machine. Uploading the torrent file. So this, we're going to assume it's uploaded to a torrent search site, right? So this is a client server model. So if you've heard of sites like the Pirate Bay and so forth, these sites get taken down quite a bit. Yeah, and they come up with a new domain. So then the announcement on tracker and monitoring the peer the peers that are interested in the same torrent. This is structured peer-to-peer with direct with a distributed hash table. And then we have the direct peer-to-peer part, where peers are connecting directly to downloaders and they're receiving the data directly. So in terms of the downloader, what it looks like from them, we again have a mix of the client server where they want to find the search for and find and download the torrent file from the torrent website search engine. Then announcing to the tracker and monitoring for peers. This is structured peer-to-peer. And then we have direct peer-to-peer where peers are directly connecting and sharing the data. Yeah. So we see that in many systems, there's often a mix in different parts of client server, structured peer-to-peer and direct peer-to-peer. Yeah. Okay. Any questions? Doubts? Oh. Okay, so we'll get through some terminology about that you may have heard and you may wonder, what these different ideas mean. So the first is the notion of a cluster computing. So these are machines typically in a central local location. So the DCC, the SSA has a cluster. There are various clusters in BOCHEP, which are basically just local physical racks of machines that are networked and can be used to solve tasks. Yeah. So this kind of idea where they're locally accessible. If we take that same idea, but we put the clusters remotely, for example, we put them, they're owned by Amazon, or they're owned by Microsoft, or they're owned by Google, yeah? And they rent the use of those machines to you. That's the idea of cloud computing. So the idea of cloud computing is this remote cluster somewhere that manages your data for you, your processing for you, and you can often rent computing resources, yeah? Cloud is often used as well just for these services that hold your data for you, like Dropbox is on the cloud and this sort of idea, GitHub and so forth. So it's similar to the idea of cluster computing, but where there's a remote service managing the machines. So just to mention as well that even in cloud computing itself can have different regions, and different regions can have different availability zones. So there can be a pretty complex structure behind cloud computing. So it's not necessarily the case that in cloud computing, there's one location with a cluster of machines that are yours, but rather there can be machines in different locations that form part of somehow the cloud computing infrastructure. So great computing was popular maybe 15, 20 years ago for certain projects. And the idea was to have machines in diverse locations. It's still quite popular for volunteer projects. So for example, maybe 20 years ago, maybe a little bit more, it was common for people to donate their idle computers, their screensaver. When their screensaver would activate, it would run a simulation, like a climate simulation or something. And that would be uploaded to whatever central climatology institute was studying different simulations of what could happen with weather. So this is no longer really used so much. I haven't seen so much of it, at least for climatology, but it is still used sometimes for finding primes. So there are volunteer projects based on great computing, where you can go and you can find primes. I think these are Mersenne primes. Someone can correct me if I'm wrong. But 2 to the n-1, I think there are Mersenne primes. So there's projects, for example, like a prime grid, where you can donate some of your computing time to help to try to find larger prime numbers. Okay? So what happens with this, there are all these computers and all these devices contributing, volunteering a certain amount of computing power to be able to test the primality of certain values of n for 2 to the n-1, right? So they give you the software, they tell you, and you just provide the computation power. So in terms of physical locations, we have cluster computing, typically centralized, local. Cloud computing, typically centralized, but sometimes it can be different regions. It can be decentralized, remote. And grid computing is heavily decentralized, right? We just have all these diverse devices and computers that are running on a particular project and remote again. Okay. Any questions or doubts? Nope. Okay, so we're going to get to a little bit of preparation for lab 2. So in the first lab, we worked with local computers. In the second lab, I want to give you a taste of a distributed system, an abstract distributed system. So the simplest and how you could get from your one computer to being able to network and communicate across several computers. So what we're going to do is sort of a simple but effective distributed system in terms of teaching some principles of distributed systems is we're going to implement a messaging system, like an instant messaging system. So effectively, you're going to be running some code where you can connect to other people's computers in the room and send them messages and receive messages and print them. Yeah. How are we going to do this? The easiest way, one way would be to unstructure, right? So, okay, let's get aside from that for a second. So how do we do this? How do we build a messaging system? So we have our computers, we have all these different computers, and we'd like them to be able to send messages to one another. The easiest would be we all open up WhatsApp or something and just use that and we're done. Yeah, but that's cheating, right? We want to get there from first principles. So we're going to need a network. We're going to assume that we're connected to the same. I hope to get a router. If not, it might be difficult to get the lab running. That hasn't worked the last 2 years, but we've had a look in previous years, but we'll try. We'll see. So we're going to need a network. You're going to be connected via Wi-Fi to the same router, right? With that, you will have an IP, at least local IP for that router. So you should be able to talk to other devices on that router through TCP/IP. Yeah. So we can send somehow internet bits and bytes, right? So what's the next thing we need? We need something built upon TCP/IP. So the paradigm we're going to use, we could try to use the web. We could try to build like some sort of API and then have something running on local host and blah, 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 but we're not going to do any of that. We're going to use a method called remote procedure call or remote method invocation. So the idea of this is that you have code that you've implemented running on your laptop, and you can let other people call that code. So essentially, you can call methods of code on other people's computers. Okay. So obviously, it depends on what you've coded. If you've coded a function to delete all the files off your hard drive, that's not a good idea. But if it's something like just print a message that was sent to me, we should be okay, right? So we're going to be using that. So we have some remote procedure call. So we have some programming language. We have some way of implementing something that people can call on our computers, and we can call the same thing on their computers. Yeah. Now you need the information of IPs. You need to know at what address can I contact different people, right? So how can we coordinate that? Yep. So we could have, let's say we nominate my computer in the room as the central server. And I implement a different kind of application that's not for messaging. It's like a directory. So you can go and you can get a list of all the people connected, and then take that and you have their IP address and you have their username, so you know who it is, and you can send them messages, right? So the benefit of that is it would be quite a lot more efficient, right, than the other alternative. What would be the other idea? Is it essential to have a central machine here? No, we could go the other way, which is. Yeah, so what we call like unstructured, right? So you're sitting together, you could share your IP addresses and your information, and we could go through the room where you connect to neighbors and maybe people bridge between the different sections. And then we hope that there's a path, somehow everyone is connected in the room, right? So if you wanted to message somebody, let's assume you knew their name, or you have to know something, some description of who you want to describe, but not their IP address. Then you could ask in the network, and maybe it would propagate from here in the unstructured network and maybe get to the other side of the room until it finds someone and the information comes back. Yeah. So that would be the unstructured way. Yeah. So the unstructured means that we have maybe better privacy in the sense that we don't need to all upload our details to a central machine. Yeah. So we can maintain more information about more control over what we share. But it's a lot more complex and inefficient somehow. Yeah, it's going to be a lot slower to find the information. So we could probably, I mean, we could probably try the other one as well, but the one we're going to implement in the lab will be a central server. So I'm going to have, my machine will act as a central server. The first thing you'll do, it will have a directory of all the details. You're going to send your details to the machine, and you're going to send your IP address and a username. So your IP address, your internet protocol address is the ID of your machine, or the address of your machine for being contacted via the internet, right? So I'll give you my IP, I'll write it on the board, and then you're all going to connect to me, and that we use that to bootstrap the peer-to-peer network. Yeah. So then you as peer machines, then you can send your details to the directory, get the details of other online users, and then you can start to message those users. Yeah. So the first part of kind of bootstrapping the peer-to-peer system relies on a central directory, and then the rest will be purely peer-to-peer. When you message each other later, once you have the IP address of the person you want to message, it doesn't need to come through my machine. Yeah, so essentially that part will be direct to that person. Yeah. So this is what we're going to implement. So how can we design a system? I think this was the way the slide was. I think this was the question was supposed to appear before the answer. Sorry, because this is the answer. So how do we design a system such that peers can find the IPs of other peers? We're going to use a central server, and peers can send and receive messages to and from other peers later directly between themselves. Yeah. Questions or doubts? No? Okay, so what programming language are we going to use? We're going to use Java for this. I don't know if there's actually a remote procedure call in Python. We all have to use the same one. So because we're going to be calling the language, the function on the other machine, we're going to use the same language. Other options would be, well, Corba for Java, which is a lot older, or what's called RPC in C, remote procedure call. So using RMI, or its analog in different programming languages such as RPC and so forth, we can use it to build distributed systems from the ground up on top of TCP/IP, on top of the internet protocols directly. And this is why it's useful. Yeah. So essentially, we can use it to build this sort of application in the classroom without any HTTP or web or APIs. Yeah. So how does Java RMI work? We're going to have a brief introduction, and then we can end the class with that. So we have a client and a server. The idea is that the server is going to implement some sort of function, right? So it's going to be, for example, the server for the central directory here will host a list of all of the users and their IP addresses, yeah, for example. Okay. So the server has the code implemented. So in this, I have to implement some sort of directory in Java where you can insert new people, remove people, whatever it might be. The clients, that would be you, for example, you will want to call the code here to be able to insert yourselves into the directory that my machine is running in Java. Yeah. So the client wants to call Java code on the server, wants to call a function, hey, insert me into directory. So the client might also need to send arguments and receive a return value. Possibly there's a typo. Okay, so RMI is remote method invocation, and the idea is that we can call methods on a remote machine. Effectively, the client can call methods, Java methods on the server. There is here the notion of a stub and a skeleton. For the client to be able to do this, they have to share some information about what the server implements. So both the client and the server have to agree on an interface. Yeah. So if you've used, for example, APIs before, you have an API documentation. It tells you what the server implements. Yeah. So you can say, oh, I need to send to this API, I need to send these parameters, and then I'll get the results I want. This is similar, right? So they somehow need to share an interface. So how do they do that in RMI, or in remote procedure call in general? They use stubs and skeletons that are connected via a network, right? So the stub essentially sends a request to the skeleton. It sends it over the internet, and it takes care of serializing any arguments. So if you have some arguments that are passed, it's important that they be serializable, which means it can be converted into zeros and ones and sent on the network and transfers those arguments. The skeleton will pass the call from the stub onto the server implementation. So the server deserializes the arguments and passes them to the implementation, runs that, and then if there's some sort of response, it will pass that back to the stub. And the stub takes care of deserializing or taking the zeros and ones and then parsing it into whatever the object is that was returned. Yeah. So essentially they allow for transparently, more or less, running Java code over the network. Yeah, so you can have all these different methods implemented on all these different machines, and you can have machines that remotely call a specific function on a given machine. How does this work for stubs and skeletons? Essentially, they will use the same interface. So in Java, here is an interface. So if you don't know so much about Java, an interface here, what we're doing is just declaring what the signature of the methods are. Yeah, so we're just saying, this is a method called create user. It accepts the user, it returns a Boolean, and it might throw a remote exception. It doesn't give the implementation. The stub and the skeleton, they don't need the implementation. They just need to agree on the interface. Yeah. Like if you use a web API, you get some details about what arguments are passed, what it will return, but you don't get details on how it's implemented. Yeah. So you just use the interface as the documentation for what the methods are and what their signatures are. And the client and the server need to share this interface. If they don't, it's not going to work. Yeah, this is the coordination needed between the client and the server. The server then implements the interface. So we have the same thing. Again, what's important here is we have the same methods, but now we've implemented them. Yeah, and the server has to do this because the server is going to run the code, right? So the server has an implementation of this interface. I think there's some problem here, which is I use the hash map. Some students a few years ago pointed out that this hash map is going to be a problem. Should be synchronized because multiple users are using it, so it should be a concurrent hash map. But yeah. So it's a very observant student, completely correct. So okay. The key point here being that the server has to implement the skeleton, and we should also be aware of concurrency. So we might have multiple users. So we have to have like thread-safe implementations of whatever we're doing here. So the server typically is implementing not just one interface, it can implement many interfaces. So how is this organized? There's something called a registry. And this registry is like a map. It's like a dictionary. So the server can add skeleton implementations with a key. So it gives a name to the things it's implemented. Yeah, so it says, okay, I've implemented this interface here, and this interface here. And a client then that knows the key can come along and say, okay, I want to get this interface SK2, and I want to call methods on that. Yeah. So it's almost like having an API with different locations for different types of functions in different paths. So this way, a server can actually have multiple things running. It can have multiple implementations implemented and available to be called from a client. So this is some code to create a registry. If I want my machine to become a server, I need to use some of these lines. We'll create a guide for this in any case later. So this creates a registry on my local machine, and then I can export some sort of implementation to that registry to say, here's a class, I have everything implemented. If you want to call this class from a client, you can access the registry, find the implementation, and run what you'd like to. Okay, so the client has to connect to the registry. It needs to know, of course, the port or the host name or IP of the server. So you need some details of where the server is. That way you can connect to the registry. So if you wanted to connect to the directory I'm going to host on this machine here. Oh. Yeah, it's all good. Okay. So if you wanted to connect to my machine here, you're going to need to know my IP and port. Yeah. So what port I'm running the registry on. I start a registry here. I implement a directory where I'm going to store the details of usernames and your IPs. To connect to the server, you need to know port and IP I'm running the registry on. That will give you access to this registry here. And the next thing you're going to need to know is what's the name of the implementation you want. So we'll use a standard name like directory. We'll keep it nice and simple. Yeah. So you say to the registry, okay, I want to get the skeleton or the stub with that key, this directory key. It's just whatever string we agree on. Yeah. Then you'll receive information about that, and you can start to call methods on my machine directly from your machine. So let's say the client here is interested in SK2 as a key, skeleton 2. Then the registry will return that implementation, and that will create a stub. Yeah, the kind of client view of the interface. Yeah. So this is some code to connect to a remote registry. In this case, I guess my machine or server.com, the host name on port 1985. And we are going to use the stub name mensaje to get the implementation that uses that key in the registry. Yeah, so here we have the line where we connect to the remote registry, which we will be calling to connect to my machine. And then we call some method on this interface. So we look up in the registry, we look up the stub name, we use the key, and that gives us back an interface that we can then call methods on. And then the client can call remote methods. So once they have access to the stub, they can call whatever methods they see in that stub with whatever arguments are valid for that method. The stub will serialize the arguments, pass them over. The server will run the actual code on its machine, and it will return whatever the response might be. Yeah. So in this case, concatenating A and B would not be a good idea to have to send that over the network, because the network costs would be a lot more costly than the concatenation, but for the example, that's okay. Okay, so how does the client call the remote methods? Once it has this stub that it got from the directory, the stub is like any other object or class or in this case object, right, that you can call methods on. So you call this as if you can call methods on this as if it were a local object. Yeah. So stub.create user, stub.get directory, stub.remove user with name, whatever is implemented, you just call it as if it were local, but it will be executed on the remote server every time. Yeah. So when you implement Java or MI, or when you implement remote procedure call in general, there's a couple of things to remember. The first is that remote calls are passed by value, not passed by reference. So if you pass a reference to something like a map, and then on the server receives the map and starts inserting things into it, that doesn't change the map that was sent on the client side. Yeah, they're not synchronized. So if you pass something and it gets modified, those modifications are not naturally going to be seen on the client. Does that make sense? Yep. That's important to remember. Everything passed and returned must be serializable. There must be some method that allows you to turn whatever object you want to send as an argument or as a return value. There has to be a way to turn it into zeros and ones, because it has to be serialized on the network. So you hopefully know about the idea of serialization, but if not, it's just this idea of taking maybe a list, a map, a hash table, whatever it is, and if you want to send it over the network, you have to translate it into a sequence of zeros and ones, and have a method on the other side of converting from the zeros and ones back into the object in the programming languages. Marshalling and demarshalling, or serialization and deserialization, this is called. Every stub and skeleton method must throw a remote exception. Like we saw before, we can never entirely rely on the network. So in the case of a network exception, we need this remote exception for that. And also, if there is a server problem, it can use the remote exception to explain what that problem is. Server implementation can only throw a remote exception. So if I want to throw some exception here, I have to pass it into a remote exception, and then I can put whatever I want, a legal arguments exception or whatever other exception. Okay, so that's a warm up for the labs, just to explain some of the concepts we're going to see. We'll take it step by step in the lab. If possible, it would be great to come on Wednesday, because the idea is that we're going to implement, to come to the room, because we're going to implement an instant messaging application in the room. It's going to be a little bit less interesting at home, because you won't be able to message other people, because everyone here has a local IP address, but not an external IP address. You're not going to have an IP address that other people in other places will be able to access, right? So we'll set up something so you can do it at home, but it will be more of an academic exercise. If you come to the class, and if we get to the end of the session with everything implemented, we should hopefully be able to try the messaging service. The messaging service is heavily dependent on the network. So I'm trying to get a router so that we can control that a little bit. If we all connect to different networks, it's not going to work. If we all try to connect to the same network, it can be tricky, as some people might not have access, and sometimes there's firewalls and so forth. So but we'll try to get it working. It's worked very well in some years. In other years, it's failed spectacularly. So it should be interesting to see what happens. If it fails spectacularly, there's still things you can do, like message yourselves, which is a little bit boring, but you'll at least see if it's working or not, right? And you'll get a flavor of the solution. Questions or comments or doubts? So after this week, we're going to start to look at our first distributed system for processing data, massive data, which would be Hadoop. So we're going to look at MapReduce Hadoop in the third class, and we're going to start a new module, right? So we're kind of covering some foundational concepts. Yep.
Is there an object that is not serializable?
Yeah. So in Java, the question is if there's any objects that are not serializable. So if you create a custom object, you create your own class, and if you don't state that it implements serializable, then it will not be serializable by default. So if you have your own class and you create an object of that, you have to in your class make sure you specify implement serializable. And you don't have to do anything else, although sometimes it will ask you for a version of the class. It'll ask you for what version of the class is this. So it'll generate a warning or something. So by default, if you create a fresh class, its objects will not be serializable. But once you add just implement serializable to the signature, it should be fine. Yeah. Other questions or doubts? Okay, see you on Wednesday. Any questions in Zoom? No. See you in the chat. Okay, see you. And all good. Okay. So see you on Wednesday. Bye bye.